you. Let's send Steve again. So the next talk is by Nicole at SimulatedCatalogs forCOSMOS-Web.
Okay, thank you. Is the mic oriented okay? Everyone can hear me? Yep. Okay. So I'm Nicole Drakos. I'm a postdoc here at UC Santa Cruz. And I'm going to be talking about COSMOS-Web, which is another JWST survey. Okay, so even before the previous talk, you probably have heard a little bit about JWST, finding a lot of high redshift galaxy candidates. There's been news articles. I just pulled a few titles about finding all these high redshift galaxies, and then some pushback about maybe these aren't as distant as they seem. They could be due to dust, for example. And then there is the article that all my friends and family want to send me about JWST, about, is this getting very blurry, or is it? Oh, you're adjusting it. Okay, got it. Okay, all right, thank you. Yes, I was just, thought it was me for a second. Okay, right. And then if you're not paying attention to the news, you're probably reading AstroPH a lot. And these are the top 5 voted papers on Benty fields for the last month. And if you go and look, I think something like the first 20 papers that have been the top voted papers are all basically JWST looking at high redshift galaxies. And there are a lot of surveys coming out with Cycle 1 JWST looking at these high redshift galaxies. So this is a plot put together by Brant Robertson in his review paper summarizing them. And see, we've got Sears down here, and this is COSMOS-Web, which I'll be talking about. And they're complementary. So they follow this typical wedding cake structure where you have your deep but narrower surveys at the top. In the middle, you have things like Sears and Primer, and then the bottom rung of this cake is COSMOS-Web. This is the proposal. Just point out that it was originally COSMOS-Web with 2 Bs, but with the controversy with James Webb's name, the second B's been dropped. This is led by Jehan and Caitlin, and it is the largest Cycle 1 GEO program. And so there's roughly 50 people on this team, and I just wanted to highlight the UCSC involvement. So Brant Robertson is part of the management team and leading the machine learning working group, and I'm leading the simulations working group. Right. So in gray here, this is the Cosmos field. JWST will be this blue square here with NIRCam, so this is 0.6 square degrees. It's contiguous. It goes down to about 28 magnitude in 4 filters. And then there's also in parallel MIRI, which overall covers, so that's shown in orange here. That's about 0.2 square degrees, and it goes down to about 24 magnitude. And there's 3 key science goals of COSMOS-Web. The first is to study the epoch of reionization. In particular, map out the environment around some of those early galaxies. The second is to look at rare quiescent galaxies. And the third is to constrain the stellar to halo mass relation. And there's all these other potential science goals that can be met with the data. So this is just pulled from the proposal. I'm going to focus on the epoch of reionization. So just to remind everyone, this is a timeline of the universe. My slide credit looks like it's cut off, but this is from Brant Robertson. Early in the universe, we had the Big Bang, and then the first picture of the universe is from the CMB. After that was the Dark Ages. Towards the end of this, the first galaxies began to form until we reached the galaxy-dominated era that we live in today. So there's 2 main transitions, recombination and reionization. So reionization, to remind everyone, is around redshift 6 to 12. The IGM goes from being neutral to ionized, and you have this transitionary period where you have these ionized bubbles. And this was talked about a lot in the previous talk. One of the main things that we want to constrain is the UV luminosity function. So these are the current best constraints from Richard Bowen's recent paper for the UV luminosity function out to redshift 10. And so you can see on the bright end, there's these very large error bars. And this is because the number counts are very low at these luminosities, so it's hard to constrain. Where on the faint end, it's hard to go past, say, -17 for high redshift galaxies, just because they're so faint and hard to detect. So COSMOS-Web is really going to help with this bright end, just because it has that large area. So here is a plot comparing the number counts between some different surveys. So for example, JADES here shown in yellow. This is how many galaxies JADES will get in total between redshifts. So this first column here is between redshift 6 and 8. But you can see, if you look in white, those are the bright end there. So there'll be about 400 and something like JADES. So on that bright end, COSMOS-Web will get an order of magnitude more galaxies. And this is also really important for understanding the environment around these early galaxies. So here, this is showing, so this plot here, this is a slice from a simulation at redshift 7. Blue is the dark matter density. Black are the galaxies that COSMOS-Web might see. And then in red are the ionization regions. And you can see this COSMOS-Web field here, this is 0.6 square degrees, is going to capture multiple bubbles. Where up here on the top, these are footprints from other surveys. They aren't large enough to get those multiple reionization bubbles. So the plot beside shows a density reconstruction just using the galaxy catalog. So you can see that by having this galaxy catalog, you can get an idea of whether they're in a high density environment. And then you can say something about how their properties depend on environment. Here on the right, that's just showing the same thing, but at redshift 9. For those of you that are interested, COSMOS-Web data has not started being taken yet. We'll get about 1/20th of the field by the end of this year, about half the field by April, and then the full field by January 2024. Okay, so for the remainder of the talk, I'm going to focus on simulations, which is the area that I work in. And simulations play a pretty large role in these kinds of surveys. First of all, they're important for planning surveys, for designing them, writing proposals, understanding what kind of science returns you can get from different surveys, for preparing for the data, developing pipelines, for analyzing the data, understanding things like completeness corrections, and then finally for constraining physics. So by looking at different simulations and different models that make different predictions, you can try to untangle what the underlying physics are. So this is a paper that came out earlier this year, written by me along with Brant Robertson. And this is the deep realistic extragalactic model, the DREaM galaxy catalogs. This was specifically meant to look at Roman Space Telescope, but it actually turns out to be really well suited for COSMOS-Web as well. It covers 1 square degree, goes down to 10 to the 5 solar masses and out to redshift 12. And as I said, it makes it ideal for looking at COSMOS-Web. So this is a brief summary of how that model is put together. They are based on dark matter simulations to make sure we get the large-scale structure correct. The galaxies are assigned to each halo just using abundance matching. And then we wrote some code to put this into a light cone. So since simulations give you these discrete snapshots in time, you need to stitch them together to make it what you observe. So this is just if you're here at 0, 0 and looking out into space, you see this wedge of galaxies. Every galaxy was assigned a morphology, assuming they're SIRSIC. And then every galaxy was given a spectra using FSPS. And the spectral properties were chosen so that we could reproduce observations. So this is a redshift 6 galaxy, just for example. In the red here, these are the COSMOS-Web NIRCam filters, and this is the MIRI filter over here. So the catalog is publicly available on my website if it's useful for you. It contains positions, masses, morphology, photometry, as well as all the underlying dark matter halo properties and more. And we did our best to reproduce some observed quantities, most notably things like luminosity functions, galaxy clustering, and the cosmic star formation rate density. And so this is an image that looks a lot better on my screen, put together by Bruno Villaseñor. So Bruno is a graduate student here that is finishing next week, and he put this together using GalSim. So this whole thing is 0.6 square degrees, and I'm just going to zoom in on that top corner there. Which that looks maybe a little bit better. And you can just see the huge number of galaxies that will be contained in this field. So if we want to relate this to some predictions for how many galaxies COSMOS-Web will see, and these dotted lines are how many galaxies there are in that catalog over that 0.6 square degree as a function of their mass in different redshift bins. And then looking at the depths of COSMOS-Web, that translates to these solid curves. So from this simulation, it looks like it'll be complete above about masses of 8.5, 10 to the 8.5 solar masses. And then, so for the first data release, just dividing that by 20, that means there'll be a few hundred galaxies during the epoch of reionization, with maybe a couple above redshift 10, assuming these number counts are realistic. Then by April, we'll get about 10 times that amount. And then finally, with the final data release, we'll have about 10 to the 4 galaxies, with maybe about 20 are expected to be above redshift 10. I will point out these higher redshift estimates are very dependent on the underlying assumptions in the simulation, since we don't actually have really good constraints about how many galaxies there actually be at those high redshifts. And this is how that translates into luminosity functions. So these different panels are different redshifts. The black are our current constraints, and here this is the number of data points that go into those constraints. The blue is from the DREaM galaxy catalogs at the COSMOS-Web area and depth. And I didn't put on completeness corrections, so you can see they turn over here at the faint end. But really what to point out is that there's the very small error bars on the bright end. So here they're smaller than the width of the line. So given that the area is large enough that the cosmic variance is quite low, and there'll just be a lot more objects on that end of the luminosity function. We'll get pretty tight constraints on that bright end of the luminosity function. Okay. So finally, just want to say some of the stuff I'm working on with the DREaM Galaxy catalog. So I have a more complete photometry catalog containing things like the HST photometry that is available, in the Cosmos field. That's not on my website, but if anyone's interested, you could just reach out. I'm looking into making possibly emission line catalogs as well. I'm also working on modeling reionization. So this is a plot where I've put a reionization model into the catalog, and this is the neutral fraction in black that is from the catalog, and then these points are different observational constraints. So I'll be looking into varying that model and seeing how that translates into predictions and how well we'll be able to constrain that with surveys such as COSMOS-Web. And I'm also working on test images for the COSMOS-Web collaboration. And then in the longer term, we'll probably put in some lensing as well into those images. Okay. So in summary, COSMOS-Web is going to be very exciting when it comes out, particularly for things like the bright end of the luminosity function. Simulations, which is where my area of work, are very important for these surveys. And then specifically, I talked today about our DREaM Galaxy catalogs, which are online, and you're welcome to look at if they would be useful for you. And we predict that COSMOS-Web will be able to find more than 10 to the 4 galaxies in this epoch. All right, and there's more to come from the DREaM Galaxy catalogs. If there's anything you're particularly interested in, I'd be very happy to talk to you about it more. And thank you very much.
Thank you, Nicole. Do we have questions?
Hi, thank you for the very nice talk. Could I ask how you just like? So you said you assign morphologies and spectra to each of the galaxies. Is there is this like a random thing, or is this something that you do dependent on some other property from the simulation?
So it's mostly semi-empirical. So the morphology, for example, that was mostly based on some work by Christina Williams. So she wrote a paper. She has some software called Jaguar looking at Jade's predictions. So it's basically from HST observations looking at what scaling relations you expect and sampling off of that. And then as far as spectra goes, so the spectra, as I said, were generated using FSPS, and that has a few free parameters, things like redshift, stellar mass, but then also star formation history, dust, etc. So with those, they were constrained to try to produce things like the star formation rate density evolution or the mass metallicity relationship. So we left those parameters free and then chose them in a way that we could reproduce a number of different observational trends.
Great, thank you.
Another question? Yes.
Do you include a connection between the black holes and galaxies to have a prediction also of the AGN distribution? How would you see them within the data set that you're expecting to get?
We do not include AGN or anything like that. That is something that we've talked about doing is, taking into account AGN scaling relations and then kind of just painting them on top and making predictions from there.
Because locally there's 10% have some sort of AGN activity. I don't know whether it's higher or lower in the past
Right.
predictions, but you can imagine that the super bright end might be truly affected by that.
Yeah,
component.
yeah. It's a very interesting point.
Anything else? If not, we can go to the coffee break, and we'll be back in half an hour, so that's 11:30. Let's thank Nicole again.